Good morning.
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 Morning. Yep. Okay. Now, guys. Now, before we continue, any questions? Did you guys try the remaining questions for chapter 8? Or the questions in the exam review? Okay, any questions you want to ask about?
Number 291.
291?
Yeah.
Okay, sure, honest. 291. Let's see. So you say question 291, and you find that on page 484.
Yes.
Okay, good. So let's see. Now assume that the frequency of sound with greatest power emitted is 5 megahertz. However, the pulse contains acoustic energies as low as 3.5 megahertz and as high as 6.5. Yeah, okay. What is the bandwidth of the transducer? Yeah, okay. So my idea what this here is, that is the main frequency. Did you get that? Also known as the resonant frequency.
Okay. That's why. Okay.
Right, okay. So this here is okay, that's your lower frequency. And this one here is okay, that is the highest frequency. So actually, that's okay. You didn't really need to know this frequency to calculate the bandwidth. You just subtract these two, and what you have as a bandwidth? 3 megahertz. Because 3.5 subtracted from 6.5 becomes 3.
Okay, yeah, that makes more sense. I was trying to figure out how the 5 fit in there.
Clear? Okay. Okay. And they may just, yes, okay, confuse you by saying, yes, okay, greatest power or something. You just look at, okay, as the units. Okay, so this was your main frequency. This was your minimum frequency. This is the highest frequency. So what you need for your bandwidth on main is, okay, just subtracting these two from one another. Or 3.5 from 6.5. And that gives you 3. Did that make sense?
Yes, thank you.
Good. No problem there. Anybody else? Anybody else with any other question?
Can we do number 300?
You said 300.
Yeah.
No problem there. Okay. So 300 is okay. Where is the best estimated propagating speed of the ferroelectrical element of a transducer used in a typical diagnostic laboratory? Now, here what they say is, okay, yes, best estimate. Okay, of the propagation speed. Of, now here is okay, they used another term. It says, okay, ferroelectrical element. Clear? Okay. This thing here is just another name for, yes, okay, your PZT, your active elements, or what we can call is, okay, the crystals. Clear? Okay. And what we said yesterday that, okay, yes, the speed of your active elements or speed of sound through the active elements or anything between 4 to 6 millimeters per microsecond. Did that make sense?
Yes.
Okay. So 4.0 is the same as 4. Clear? Okay. Millimeters per microsecond. So yes, okay, this is still, yes, okay, propagation speed of your active element. Well, what they said was, okay, it's a roughly 5 times greater than that of soft tissue. Although else, okay, soft tissue had a speed of this much. Okay. Anything else? So this number or this value here was actually just, okay, given in the text. Yes. Anybody else? Yes, guys. No questions? Okay. Okay, guys. Since at this moment nobody have any questions, then let's just continue them. And the next chapter is going to be chapter number 9. Okay, and I hope all of you are aware that, okay, yes, chapter 6, chapter 7, and 8 are the chapters on your quiz. Clear? Okay,
Yes.
good. Now, guys, chapter number 9. And what is that chapter 9 is about, or says that it is about, is sound beams. Yeah, okay. Now, why do we call it sound beam? Mainly because, okay, here is, okay, it's going to be made up of sound waves. But the reason that we call it a sound beam is because it mainly, as okay, has the similar characteristics just as a light beam. Okay. And two things that we will be, as okay, talking a lot about in the upcoming questions. One of them is going to be, as okay, a sound beam, and that is going to be, as okay, the pulse, or we can say it's okay, sound pulse. Or we can say it's okay, we already have talked quite a lot about the sound pulse. So the next entity that we will talk about here is going to be the sound beam. Yeah, okay. And there are going to be, as okay, certain features of your ultrasound that is going to mainly, as okay, be determined by the sound beam. Okay. Okay, but please keep in mind that, okay, yes, within the sound beam, it's okay, you will still have your pulse. So it's not two things that can be separated from one another. Okay, but we will talk about it, okay, because each of these here is okay, will determine their own entities as far as, okay, as an ultrasonic image is concerned. Okay, so our main discussion, or to begin with, is okay, we will mainly, is okay, talk about, is okay, what is it that a sound beam looks like. Okay, and we're going to take that as a single beam produced by a transducer, assuming that that transducer only has one single PCT. Is that clear? Okay. But what we know, or what we actually is okay, we'll get to know that most of our transducers are going to have multiple PCTs. But if you have the general concept of, okay, yes, what one single sound beam would be like, you can mainly say, okay, from one PCT, that's just going to be as, okay, each of these PCTs will be producing their sound beams. Clear? Okay. Which are going to, as, okay, be looking exactly like this single beam here, but just all together. Okay, so our first topic, and yes, okay, talking about a sound beam is what we can guess, okay, the anatomy of a sound beam. Okay, and in this case, yes, okay, we just going to, no, so let me just make it. We're just going to assume that this is mean that's okay, going to be as okay. When we talk about a transducer with a single PCT. Which in this case is going to be as okay, what we can call as okay, a disc shaped PCT. Okay, so guys, this here is going to be your beam. So we go like this, and it will go like this. Then we can say, okay, we have this area here. And then we can say, okay, we will have this area here, like this. So that is going to be, yes, okay, we can say, it's okay, the anatomy of an ultrasound beam. Okay, where we actually say, okay, we'll have different zones or regions, if that's what you want to call it. So our next point is going to be, yes, okay, to name each of these regions here, or zones. So the first part of the beam, or this here, that is going to be, yes, okay, what we'll call the near zone. Clear? Okay. This near zone here is okay. Now again, yes, okay. What you will see is that, okay, yes, one thing may go under more than one name. So this near zone here is okay, can also be called the Fresnel zone. Yeah, okay. But what is the near zone? That's mainly as okay, the part of the beam. As okay, immediately as okay after it leaves the transducer.
Mike, can you repeat what the other name is for it?
Fresnel, Fresnel.
Thank you.
Yeah, is that better?
Yeah, thank you.
Okay, no problem. Yeah. So your near zone can also be called the Fresnel zone. Yeah, okay. And what is it the Fresnel zone is? It's mainly as okay, that zone or that area of the beam of your ultrasound as soon as it emits the, or yes, okay, emits, or yes, okay, from the transducer. Did you guys get that?
Yes.
Yeah, okay. Now, what I just will do here is see that this point here, or we say it's okay, green, or brown, sorry. That is going to be, it's okay, what we can call the focus. Clear? Okay. We will call that the focus, or this can also be called the focal point. Did you get that?
Yeah.
Okay. Whereas we have here is going to be as okay what we call the far zone. Okay. And the far zone can also go under another name as Fraunhofer zone. Yeah, okay. Now near zone, as Fresnel zone, or could also be as okay called the near field. Far zone could be Fraunhofer zone or the far field. Now, guys, what we see is that on either side of your focus or your focal point is there going to be a zone that is called the focal zone. Yeah, okay. And if you look at it, we can mainly say that, okay, as half of your focal zone. Half of your focal zone is in the near zone, and other half of your focal zone is in the far zone. So focal zone is going to be a zone around the focus, which half of it falls into the near zone, half of it falls into the far zone. Did you guys get that?
Yeah.
Yeah.
Good. Any questions so far? Okay. Now, guys, yes, okay. When you look at the beam, what we see that happens to the beam in the near zone. So we can say, okay, in near zone. Okay, what is that happens to the beam? It gradually narrows down, right? Right?
Yes.
Okay, because here you can see it's okay, the beam has a greater diameter, here it has a smaller diameter, here it has a smaller diameter, here it has a smaller diameter, so on. So it's gradually, it's okay, going to narrow down. Okay, and this narrowing down, that is mainly as okay, what we would call convergence. Right, okay. So how is it that a beam behaves in the near zone? It narrows down. Clear? Okay, so immediately, yes, okay, the beam is going to have a greater diameter. As it goes deeper and deeper and deeper and deeper and deeper, as long as it is in the near zone, what's going to happen to the beam? It will narrow down. Did you guys get that? Yeah, okay. So this narrowing down, that's what we also as okay, we refer to that, okay, as the beam is going to converge. Where does the beam converge? In the near zone. What is another name for the near zone? It can be called a near field. It can be called the Fresnel zone. Clear? Okay. And, well, okay, as what we actually is okay, will say is that, okay, yes, at the focus or at the focal point, we can say, okay, this is the point of the beam where it is at its narrowest. We can say it's okay diameter. Is that clear? Okay. So how would you define as okay the focal point of a beam? Well, you can say, well, okay, that's going to be the point and the beam where the beam is at its narrowest. Where does the focal point falls? It falls at the end of your near zone. So the point where your near zone ends, that point is going to be referred to as the focus or the focal point. Did you guys get that? Clear? Okay. Okay. So what was all this? All this here is okay, was your near zone. What happened in the near zone? The beam gradually narrows down, right? Did that make sense?
Yeah.
Until it reaches just okay the point where the beam is at its narrowest diameter. Clear? Okay, and what do we call that point? That's what you will call as okay, we can refer to as either the focus or we can refer to as the focal point. Clear? Okay, so that's okay. When looking at the beam, what is going to be the focal point or focus? Well, okay, that's going to be the point in the beam where the beam is at its narrowest diameter. Where does it fall? It falls at the end of your near zone. Did you guys get that?
Yeah.
Yeah, okay. Now, what happens after the focus? Where the beam has reached to its narrowest point, the beam is then going to, yes, okay. We can say it's okay, start to spread out. Clear? Okay. So what happens in the, and that's made as okay, that going to be as okay, what we'll call the far zone. Clear? Okay. So yes, okay. In the far zone, what is going to happen is that, okay, as the beam is actually going to, yes, okay, we can say, okay, spread out. Yeah, okay. Or this spreading out is what we also as okay will refer to as that the beam is going to diverge. Did you guys get that?
Yeah.
Right. Okay. Okay. So what's going to be the far zone? Well, we can say it's okay, the area that comes after the focus or focal point. Clear? Okay. What's going to happen to the beam in the far zone is that it will spread out. It will diverge. Okay. So what actually happens to the beam in the far zone is divergence. Did you guys get that? Okay. And at as okay, because that's okay. At a certain yes, okay, point around the actual focus point that we had a zone that we call the focal zone. Okay. That we call a focal zone. Clear? Okay. And one thing that you guys will need to remember is that okay, as half of that focal zone falls into the near zone or Fresnel zone or near field, where okay, the other half of your focal zone falls into the far zone. Yeah, okay. Let us just say that, for instance, okay, just to explain that, let's say that, okay, as our focal zone was 2 millimeter, which mainly means, okay, from here to here, the distance was 2 millimeter. Okay. But then if you ask, okay, how much of the focal zone will be in the far near zone? Well, okay, yes, that will be 1 millimeter. So the first millimeter of your near zone will fall into of your focal zone will fall into the near zone. The remaining 1 millimeter of the 2 millimeters here will fall into the far zone. Did that make sense? If they said that your focal zone, for instance, okay, was 4 millimeters, then it's going to be the same. Half of that in the near zone. So then yes, okay, 2 millimeters of the 4 millimeters of your focal zone falls into the near zone. 2 millimeters of your 4 millimeters of the focal zone falls into the far zone. Did you guys get that?
Yeah.
Good. Okay, guys. I'm going to be drawing this beam here again and again and again and again. So this was near zone. We can see that, okay, yes, this part here is the focus. And then, okay, yes, on the other side, we can say, it's okay, this here is the far zone. Okay, now let us just focus on the focus. Focus, also known as the focus point. Okay. Now we can say it's okay. We can do it this way and say it's okay. This is the point in the entire course of the beam, which will have the greatest intensity. So the focus or your focal point, that is going to be as okay the point in the entire course of the beam. And what's going to be as okay the entire course of the beam? We can mean as okay from beginning to end. That will have the highest intensity. And my question is, why?
Is that because the area is the smallest?
It is the smallest. Here we go. Right. Okay. Because, oh shit, sorry. If you, for instance, okay, took the beam here, let's say it's okay, that okay, let's say that okay, as our PCT in this case is okay, had a diameter of 5 centimeters. How many mean that okay, as from here to here, it would have been 5 centimeters, and okay, from here to here, it would also have been 5 centimeters. So immediately as okay, here, because that's okay, the diameter of the beam would also have been 5 centimeters. But what is that we see that happens to it is okay, it gradually as okay narrows. So here as okay we will narrow. Let's say as okay 4.5 centimeter. Let's say as okay here it is even narrower. We can say as okay 3 centimeters, for instance. Where okay here is going to as okay be at the narrowest. Yeah, okay. Now one thing that they say that okay, if the diameter of the PCT, where we actually is okay, if you look at the PCT like this, and say that okay, it has a diameter of 5 centimeters, that will mainly mean that okay, as from side to side, this measurement here is okay, would have been 5 centimeters. Or from top to bottom, this diameter or this dimension also would have been 5 centimeters. So what they mainly say that okay, the diameter of the beam is going to be as okay, we take, if we look at the beam here at the focus in the cross section, that this dimension here was going to be 2.5 centimeter. So is this dimension also going to be 2.5 centimeter. So what they mainly say that the diameter of the beam at the focus is, or at the focal point is going to be half the dimensions of the PCT or crystal. Did you guys get that? Yes, students.
Yes. Yep.
Okay. But throughout the entire course. Yes, okay, the main reason that the focus or your focal point is going to, yes, okay, have the greatest intensity, because that was the point of the beam that we said was narrowest. And what does it mean to be narrowest? Having, yes, okay, we can say, so in this case, okay, the smallest area. And what do we know? That intensity is inversely proportional to area. Did you guys get that?
Yes.
Good. Now let me ask a dumb question. What kind of intensity are we talking about? Okay, guys. Can you guys name types of intensities? Anybody? Anything? I haven't killed anybody yet, so and I don't intend to start yet either. So go ahead.
Would it be the sound beam's intensity?
Okay. Let me help you guys a little bit on the. My question was, what are the two types of intensities?
Initial and final?
Okay, at least you said something. Okay. But those are not the ones.
Transmitted intensity
Mm,
and reflected intensity.
okay, that's not the one either.
Intensity coefficient.
Oh. Okay, that's fine. Okay, guys, or students, you are lost in time and space. And here's your answer. What do you call intensity in time and space?
Spatial and temporal?
Temporal. Okay, good. So when we talk of a beam, what kind of intensity are we talking about?
Spatial?
Spatial. Here we go. If you go and look back in chapter 5, and I briefly said that, okay, at that time, that, okay, yes. Fine. That case is okay. The mean is okay. J is taking okay as a beam that went straight like this, no narrowing or so on. So, okay, because in that case, it's okay. Our main goal was just to talk about maximum or peak, and average. Yeah, okay. But where is it that you have your maximum intensity? The max intensity is okay in the beam. Where would that be? Right? And it's just okay, your spatial peak intensity. Okay, where what we said was the average was that okay, as we took all this energy here, and if we had okay, as evenly distributed it out. But even if that was the case, that's okay, you will still have yes, okay, maximum intensity at the focus, because that was going to be the point where at the beam where the beam was at its narrowest. Okay. But when we talk yes, okay, intensities in relation to beam, yes, okay, we are mainly referring to yes, okay, the spatial intensity. Yeah, okay. So in the entire course of the beam here, it's okay, at least for what we have talked about so far, that we can say, okay, this point here is going to be as okay where we will have the lowest intensity. It may be as okay slightly greater here. It may get even yes, okay, greater here, but at the focus mainly because the beam, that's the point where the beam is at its narrowest. That'll be as okay where we will have the highest intensity or the max intensity in the entire course of the beam. Right, okay. Why? Because, okay, that is the point where we have the lowest area or the smallest area. Yeah, okay. How do we relate, or how is it that the relation of, let's go to another slide. All going to be the relationship between the area as okay of the beam in the beginning. Or how do we relate yes, okay, the area of the beam at the focus to yes, okay, the area of the PCT or the diameter of the PCT is that is going to be half of the diameter of PCT. Did you guys get that? So if you have PCT here, let's say it's okay. If you look at the diameter here and say it's okay. That, for instance, okay. God was, let's take another number, say 4 centimeters. Which means okay, in this case, it's okay, since we have a circular PCT, it's okay, this is also going to be 4 centimeters. That mainly meant that, okay, as if we had taken the beam at the focal point, is going to be half the diameter of the PCT, which will mainly cause that, okay, this dimension here would have been 2 centimeter, and or this diameter here would have been 2 centimeter. Yeah, okay. Have we had a smaller PCT, for instance, let's say it's okay, that the diameter of the PCT would have been 2 centimeters. And that's okay, 2 centimeters like this. then your diameter of the focus or the diameter of the beam at the focal point was just going to be half of that, 1 centimeter and or 1 centimeter. Did you guys get that? Okay. Or if you don't, well, guys, there's a picture in your book on page 132. Can you see that? Do you have your books with you? Figure 9.3. That means it's okay, tells us, or that means it's okay, that displays what we said. Did you guys get that? No, guys. Any questions yet?
No.
Okay, let me say it. This chapter is one of the chapters. Okay, I don't know why. But that's okay, where student ends up, that's okay, repeatedly coming back and asking me the same questions. I don't know what I'm doing wrong. Okay, guys. So what was a beam? Or why did we call it a beam? Mainly because, okay, it keeps on narrowing until it gets to its narrowest point. What do we call that point? We call that point the focal point, or we call it the focus. Right? And what's going to happen after the focal point or focus? The beam is going to diverge or spread out. What did we call that point? Or what did we call that area of the beam or zone? That's going to be the far zone or the Fraunhofer zone or far field. Did you guys get that? Okay. Now, guys, please PAH. Okay, that's probably a little bit too much. So, guys, what do we call this red area here? We call that the near zone. We could also call it the near field. And okay, yes, it could also be called the Fresnel zone. Did that make sense? Right, okay. And whatever, yes, okay, the diameter of your PCT was. Okay, the diameter of the beam is going to be half of that at the focal point, which is going to be, yes, okay, the narrowest point in the entire course of the beam. And since it has the narrowest point, it's going to, yes, okay, have the highest intensity. Did you guys get that? Now, another thing. Or you can say it's okay. PCT. Let's say it's okay. This is our near zone. Because it's okay, the beam reaches its narrowest point, which is the focal point, also it's okay referred to as the focus. After which, yes, okay, the beam is going to, let's say it's okay, diverge out, and we call this the R zone. Did you guys get that? Good. Now, this which is your near zone, your near field, or your Fresnel zone. Okay, but when we actually just okay say that, let's go, let's see. If you for instance, okay, measure the distance. This here, if you measure this distance, this distance is going to be referred to as, okay, as the focal depth. Yeah, okay. You can either say as, okay, the focal depth, or it can also be known as the focal length. Did you guys get that?
Yes.
So what is going to be the focal depth or the focal length? We can mainly say, okay, that's going to be the distance between the transducer and the focal point, or the distance between the transducer, or we can say the start of the beam and the focus. Did that make sense? So just look here, guys. Assume that this here is, okay, the PCT. Clear? Okay. It emits a beam. And that beam, yes, okay, gradually narrows down till it reaches its narrowest point, which will be the focus. Clear? Or the focal point. Now you can mainly say as, okay, here the distance between my face or the PCT and my hands, that distance is going to be referred to as the focal depth or focal length. Yeah, okay. But what does it constitute? It mainly as, okay, just constitutes your whole near zone. Did you guys get that? So you can say, okay, we had a greater near zone. If the near zone increased or became bigger or longer, you will have a greater focal length or a greater focal depth. Did you guys get that? Okay. Now, dear students, when you look at a scan, Now this is your screen. Let's say that this here is okay, is your image. Yeah, okay. Now just so you guys know, up here is okay, that's where you have your transducer. Did you guys get that?
Yeah.
So the top part of your image, that means that's okay where you will have the, or where you'll find the transducer. Now some of you will say, but Mike, doesn't this just okay image diverge out? Well, okay, that's just because of the shape of the image. Why and so on, why it has the shape, so on, so on, so. We'll talk more about that in a later chapter. But what you guys know is that, okay, yes, we have, let's say it's okay, different depths along the image, right? We can say, okay, this is depth of 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, and let's say it's okay, 5 centimeters. Did that make sense? Students, please respond.
Yes.
Yes.
Okay. Now, let us just assume that in this case here is okay, we set our focal point at 3 centimeters. We set our system to focus at a depth of 3 centimeters. So this is actually going to be as okay, what will be as okay, or okay, sorry. This is going to be as okay, our focus. You can say it's okay. At a depth of 3 centimeters, this is our focus. Did that make sense? Which mainly causes that, okay, yes, from your transducer to that depth of 3 centimeters, yes, okay, this is going to be, yes, okay, your near zone. Clear? Okay. And what you mainly have done is, okay, yes, you had set your focal depth at a depth of, that's okay, this is going to be, okay, your focal depth or focal length. Okay. But that is actually going to be the same as the distance of your entire near zone. Because at the end of your near zone, that's means it's okay where the beam focuses. Did you guys get that? And what remains is okay, just can say is okay, what happens after this point or after the focal point here. This was your focal point at 3 centimeters. What's going to happen then? Well, okay, yes, from here and onwards, just okay, that's where you have your R zone. Did that make sense?
Yes.
So the depth, whichever depth you choose for your beam to focus at, okay, well, okay, that point where the beam focuses at is going to be called the focus or the focal point. But you can say, okay, the depth at which it focuses, which is going to be, okay, we measure it, okay, from your transducer. This distance here is okay, is going to be called the focal depth or focal length. Did that make any sense? Okay. Now, all of you are of a younger generation than me. Right, okay. You may have seen, yes, okay, your grandpa's photo camera where he would have, okay, as a bigger or smaller lens, but where he would actually, yes, okay, to twist and turn the lens to focus. Yeah, okay. So what's going to be the whole point of focusing?
To get a clearer picture.
Clearer picture. Okay, so if you didn't focus, yes, okay, what was going to happen? Yes, okay, your picture will not be clear. But you can say, yes, okay, I have a big field. Okay, oh, yes, okay. From here to, yes, okay, a mile ahead from me, away from me. But there's going to be, yes, okay, that big area, yes, okay, there's going to be one point that I want to focus on. That is going to be your focal point. Okay, that is going to be your focal point. Now, guys, although in the beginning, or at least now, we mainly, yes, okay, just chalk off, okay, yes, having one focal point. Okay. In a later chapter, we will actually, yes, okay, talk about, well, okay, how is it going to be possible for us to keep more than one focal point in an image at the same time? Okay. Okay. So we can keep more than one focal point at the same time, or we can say it's okay, we can have multiple focal points at the same time. And if we want to, yes, okay, we can focus at shallower depths or at deeper depths as well. Clear? Okay. But to understand all that, yes, okay, you'll first need to know, yes, okay, what do you mean by a focal point? A focus, the point where the beam gets at its narrowest, its highest concentration of energy, which is going to be highest intensity. Did that make sense? Right, okay. By the time, okay, let me put it this way, guys. By the time you guys are due for your, yes, okay, are going to, yes, okay, meet up for your next quiz, we might have already, most likely, yes, okay, we'll be done with chapter 9 and chapter 10. Let's just see, okay? That we're done with chapter 9 and chapter 10. Okay. Now, what were the chapters that was going to be on your quiz?
6, 7, and 8.
Okay, good. What chapters did we do before 6, 7, and 8?
1 through 5.
1 through 5. Clear? Okay. So if I say, well, okay, guys, you guys need to study. You guys need to study. You can say, well, okay, right now, we mainly, as okay, want to focus on the chapters that's going to be on the quiz, right? Now, how do you focus on those chapters that's going to be on the quiz? You're going to, yes, okay, concentrate most of your energy, attention onto those 3 chapters, right? Yeah, okay, and say, okay, forget about the near zone, which was 1 through 5. Okay. Forget about, yes, okay, 9 and 10, which is in the far zone. Because the real chapter that we need to focus on now is 5, 6, 6, 7, and 8. Right? Did that make sense? Okay. So when you say, okay, focus, what is it that you do? You're concentrating your energy onto that point. Yeah, okay. And the more energy you concentrate onto, yes, okay, a narrow spectrum, what happens? Greater intensity. Did that make sense?
Yep.
Did it sink in? It's not a matter of just making sense. Did it sink in?
Yeah.
Good. Okay. So what are the main areas of your beam? Near zone, also known as near field, also known as Fresnel zone. What happens in the near zone, near field, or Fresnel zone? The beam converges or it narrows down. Here. Until, yes, okay, the near zone ends at the narrowest point called the focal point or focus, where the beam will have its highest intensity. Did that make sense? Clear? Okay. After the focal point, after your focal point, what do you get? What do you have? What you call the far zone, Fresnel zone, Fraunhofer zone, or far field. Clear? Okay. What happens to the beam in the far zone? It diverges. Or you can say, okay, it spreads out. Clear? Okay. So what's going to happen to the intensity of the beam in the far zone? As you go farther and farther and farther in the far zone.
It gets weaker.
It gets weaker because the area of the beam gets greater, right? Did you guys get that?
Yeah.
Good. Now, guy or students, yes, okay, and other things. And let's just put, yes, okay, most of the things that we have learned so far together. Let's say this was our PCT. Yeah, let's say it's okay, this was the near zone. We can have, yes, okay, the focus. And of course, yes, okay, we can have the far zone. Oh, probably a little bit too big. Yeah, okay. We can also say it's okay that on either side of the focus, if we had, okay, that's what we can call as, okay, the focal zone, which half of it half of the focal zone, that's okay, falls in far zone. half of the focal zone, sorry guys. Half of the focal zone, yes, okay, is in the near zone. Now let us just say that, okay, here is, okay, the diameter of the PCT, for instance, was 4 centimeters, which means that, okay, yes, this dimension could be 4 centimeters, or yes, okay, this dimension here also would have been 4 centimeters. Mainly because in this chapter here, we mean is, okay, talk about is, okay, we have a round shaped PCT, which we mainly will say that, okay, yes, at the focal point, whatever the focal point was, or whatever the focal length was, is okay. But here is, okay, our diameter of the PCT would, or of the beam would have been half of what we had here, so it will be 2 centimeters. Which says, okay, this dimension here would have been 2 centimeters. Or yes, okay, even this dimension here would have been 2 centimeters. Clear? Okay. Now let us just assume. Because, okay, what do we have? We say, okay, in the focal zone, or in the near zone, sorry. In the near zone, this distance here was our focal depth. Now let's just say that, okay, our focal depth here was, let's just take any number, it doesn't really matter, 3 centimeters. Okay, that your focal depth was 3 centimeter. Focal depth or focal length was 3 centimeters. Now, one thing that you can be asked about is, what will be the diameter of the beam here? Where you can say it's okay. Now that can be as, okay, asked in different ways. They can say it's okay, 3 centimeters off your focal point. So maybe you can say that this distance here is also 3 centimeters, which is the same as that of your focal depth. Now, what as per standard that the mainly will say that, okay, the diameter of the beam is going to be here, is going to be as, okay, the same as what it was over here. So it's okay, it's going to be 4 centimeters by 4 centimeters. Because this distance from the focal point to the point that we as, okay, talk about the diameter is the same as that of your focal depth. Clear? Okay. Whereas if they said, they asked about as, okay, what the diameter of the beam would have been, let's say at this point here. Okay, we may not be actually exactly able to say, but one thing that we can say is, okay, of course, that's okay. Here is, okay, the diameter of the beam would be greater than 3 centimeters. Yeah, okay. They may said, okay, well, okay, maybe this distance here, for instance, okay, was 6 centimeters. Then we could, yes, okay, mainly say that, okay, yes, then most likely, yes, okay, this diameter, okay, it would be greater than, well, not 4 centimeters. 3 centimeters, sorry. When I messed it up. Greater than 4 centimeters. Okay. But we could say, yes, okay, here, if they gave us a depth and say, okay, yes, 6 centimeters off the focal point, 6 centimeters off the focal point, we could then say, okay, yes, here the diameter of the beam would be 8 centimeters. But, if the distance from your focal point into the far zone is equal to your focal depth or focal length, then of course, okay, at the end of that far zone, at that point in the far zone, the beam's diameter will be the same as what it was at the transducer, or the same diameter as it was, or as we had as a size or diameter of the PCG. Did you guys get T hat?
Yeah.
Okay. So why do we call it a sound beam? Mainly because it behaves like a light beam. Have any of you ever seen a lighthouse? I knew you weren't seen one. Okay. Okay. So what is it a lighthouse does?
Emits light.
Okay. For what?
The ships.
The ships. Clear, okay. But of course, yes, okay, you can say, okay, at some point, yes, okay, that beam will dim out, right? Why? Why would the beam dim out?
It like the power ran out or like because it's spreading out.
At a certain point, yes, okay, the beam will become, yes, okay, so dim that you don't even see it anymore, right? Why would that be?
Because it's too far away. You're too far away from the source.
Okay, good. So if the distance from the source increases, what happens? What will you call that distance from the source? Yes, my dear. What will you call that distance from the source?
Oh, still me? Um,
No, anybody. But okay,
the distance from the source, isn't that the far zone or
okay. So is near zone not a distance from the source?
it is. I figured like
Okay,
near zone is
but I said
closer.
okay, okay. Listen, dear. Okay, this. I said okay. As why does the beam dims out? You said because it's at a greater distance of the source. So what will you call that distance from the source now? In terms of ultrasound physics?
Is that the focal depth?
What the hell is a path length? What happens after 3.5 miles or whatsoever is okay? That beam is not going to be visible anymore, right? Why? Why? It attenuates. It's not only sound energy that can attenuate, any energy will attenuate. We should be happy for that. Okay, now nowadays some of you says, okay, I just wish that we could get some sun. but I bet to eat anything that none of you is okay like to is okay have the same temperatures on Earth that are as there are on the sun. Do you guys know what the temperatures are on the sun? That's okay by the sun. Okay, don't even think about it. We will melt. Literally, as okay, we will melt, and that's slowly, instantly. So guys, it's not only yes, okay, sound energy, any form of energy is okay, will attenuate, but okay, yes. Okay, you can mainly say, okay, any distance in the beam. Okay. So, guys, any questions about any of this?
No.
Okay. So, dear students, this was the general anatomy. This was the general anatomy of your beam. Now, these guys, you have some pages to read on. Okay. And I will give you guys, students, that's okay, the time to do so now. Okay. And what we, okay. Take some 20 minutes to read on the quiet, yes, okay, read on the text. And when we come back, yes, okay, we will try to look at the questions together, okay? Okay. So yes, okay, there are a couple of pages. Read on those. Make sure that, okay, as you register the different names for different things. And so on, okay? So I see you guys at 10:55. Welcome back, students. Okay, so have you guys, or did you guys get enough time to go through the material? Okay. Any point that you think needs to be clarified further? Or anything that you still don't get? Nope.
So
Cool.
far, so good.
So far, so good. So you think you got everything so far?
We'll find out.
Okay. Okay, let's see. Okay. So, yes, okay, we got a total of witness says, okay, 10 questions, not 12 questions, not 10. And it's going to be as okay. All that's okay. It's two diagrams on all different pages, but they are the same. Okay, so we may just okay have this is going to be our diagram. Now we can mainly say that, okay, yes, if this here is your PCT, this is your PCT, and this is 12 millimeters, which mainly means, okay, if we looked at it, this distance here had been 12 millimeters. And or even it's okay, this distance here would have been 12 millimeters because we are talking about is okay here, disc-shaped PCT. That's what you see, right? Okay. Now what they gave us is a beam. And now this distance here, now this is going to be as okay, your focal depth. So here's okay to say that that is 8 centimeters. Very mainly because although that's okay, not given in the picture, we can say, okay, but this here is your focal point. After which, yes, okay, we have the far zone. And then you see, yes, okay, a little distance here, which is, which is 4 centimeters. Yeah, okay. So that is our sound beam. And okay, yes, all in accordance to this sound beam. Yes, okay, we have a couple of questions that we need to answer. So question number 1 is, what is the best estimate of the diameter or the width of the sound beam as it exits the transducer? So what they mainly is okay are asking about is okay, where is the width? He says, okay, this here will be the width or diameter of the sound beam as it exits the transducer. So they says, okay, if you look at the beam here, what would have been the diameter of the beam at this point here? Now we have different distances or different measurements, 6 centimeters, 9 millimeters, okay, 12 millimeters, and 8 millimeters. And mainly as okay, since at this point, yes, okay, the beam hasn't converged yet. That's why, because it says, okay, if you look at this dimension, yes, okay, it would have been 12 millimeters. Or if you look at this dimension, yes, okay, that would also have been 12 millimeters. So that is your answer, 12 millimeters. Did you guys get that?
Yes.
Right. Okay, why? Because the beam mainly has, okay, just started its journey. It hasn't started converging it. So immediately that's okay, is going to be the same as the diameter of the PCT. Now, please keep in mind, guys, 12 millimeters can also be as okay 1.2 centimeters, right?
Right.
Good. Question number 2. Now, what is the diameter of the beam, or what is the diameter of the sound beam at a depth of 8 centimeters? And a depth of 8 centimeters, that's what we have here. So this 8 centimeters, okay, where was it? If you actually can say that was going to be, it's okay, that was going to be, it's okay, your focal depth. What do we have at the end of the focal depth? The focal point. Clear? Okay. What were we said, or what was it that we said that the diameter of the beam was going to be here? Now here you actually, it's okay, you have to know this diameter here, whether it's this dimension or this dimension. You can say the width or the height. It's okay, what was the diameter of the beam or what was the diameter of the PCT? And we can mainly say, okay, that's just going to be half of the diameter of the PCT. So half of 12. So the half of 12, my dear guys, is going to be 6 millimeters. Did that make sense? Did you guess that?
Yeah.
Question number 3. Now, what is the diameter of the sound beam at a depth of 16 centimeters? Now, when they say it's okay at a depth of 16 centimeters, probably that's okay with me from here. So this is 8 centimeters. And if you add on another 8 centimeters, we can say, okay, this is going to be okay at a depth of 16 centimeters. Did you guys get that? Okay. So what we mainly can say is that, okay, yes, that the diameter of the beam is going to be okay at this depth here, which is twice your focal depth. Is that okay? Yes, it's going to be back to 12 millimeters or 12 millimeters. Did you guys get that?
Yes.
Okay, but here it says, okay, they talk about is okay at a depth of 16 centimeters, which was just twice your focal depth. So the first centimeter, 8 centimeter, what happens? The beam is okay diverged or converged from a diameter of 12 millimeters to half, which is going to be 6 millimeters. Where okay, for the remaining 6 centimeters, or sorry, 8 centimeters, is going to okay diverge back from a diameter of 6 millimeters back to 12 millimeters. Did that make any sense?
Yes.
Question number 4. Now, at what depth is the focus? Now, it's okay, although it's okay in the diagram, it's okay, they hadn't labeled that, but we can say that from our, diagram, that the beam focuses at a depth of 8 centimeters. Okay, which is just going to be as okay, saying at what depth is it that we have our focal point or our focus? Is going to be as okay the same as the focal depth. So as okay, focal depth is going to be as okay the depth at which we have the focus. Yeah, okay. Now, how could this focus here be reworded? Because that's okay. At what depth is it that the beam is going to be at its narrowest? Diameter. Okay, we're having the same answer. But here it's okay, they just talk about the focus or the focal point or they ask it, yes, okay, look, it's okay, defining what the focal point was going to be. The point where the beam is at its narrowest. Did that make any sense, guys?
Yes.
Good.
Yep.
Good. If you don't get it, guys, please ask me. Okay. And I'm not exaggerating. Even though it's okay, these questions here is okay, maybe on the midterm. I explained them again for the midterm for students. And they will still ask the same questions a couple of days before the final. So if it doesn't make sense, please ask. Okay, guys? There's nothing wrong in okay as forgetting things. That's okay. That's the okay. So that's why it's okay. Slowly and gradually it's okay. You should be as okay. Not now, not just focus on okay as oh shit. That's okay as that's in the beginning of the near zone. So we can see as okay the next question. Okay, let's see. Yes, okay. Question number 5 reads, okay, yes. What depth marks the beginning of the focal zone? Clear, okay. So what depth marks the beginning of the focal zone? Now, some of you guys may have wondered, yes, okay, what the blue was these 4 centimeters here. This here is your focal zone. What did we say that the focal zone was? Okay, yes, it was a distance of 4 centimeters. Did you guys get that? Okay, so yes, okay, our focal zone. Well, okay, that's not the answer, but that's okay, is 4 millimeters. Our total focal zone. Now, what did we say about the focal zone? Half of the focal zone is in the near zone, right?
Right.
Right, okay. So, this is most likely, it's okay, where most people get confused. So let's just look at it in this way, guys. It's for your PCT. We can say this here is okay, was your focal depth. At the end of which we have the focal point. And we had, okay, yes, the focal zone, which was 4 centimeters. Or where we mainly can say that, okay, yes, half of these 4 centimeters, which is going to be, let's see, 2 centimeters is in the near zone. And yes, okay, if you want to go, yes, okay, we can say that's okay. 2 other centimeters is going to be in the far zone. Okay, so if your total focal depth was 8 centimeters, but the main is okay, at what depth is it that your focal zone starts? The start of the focal zone is going to be okay at a depth of 8 being subtracted from 2. So at a depth of 6 centimeters, which may mean that this distance here was 6 centimeters. Did you guys get that?
Yeah.
Okay, so the depth at which the focal zone begins, based on all this, is going to be half of the focal zone is in the near zone. So that's okay, 2 centimeters off the near zone, or into the near zone. From the focus is going to be the distance at which your focal zone begins. Did you guys get that?
Yes.
Good. Now question number 8, now question number 6. All this okay on the other page, but it is the same diagram that you have. They just remade it so that you didn't have to flip back and forth, flip back and forth, flip back and forth. Okay. But what they mean is, okay, I'm just asking us here is, at what depth, or what depth marks the end of the focal zone? So yes, okay, this is the end of focal zone. Where we knew that, okay, yes, this distance here is okay from transducer to focus was 8 centimeters. Okay, because that was your focal depth. But we also say that, okay, yes, our focal zone was 4 centimeters, and half of that 4 centimeters falls into the far zone. Clear? Okay. Okay. So what's the half of 4? That would be 2. So here is okay, we mean is okay, you can say that we just are going to, sorry. Let's see, it's okay. Add these 2 centimeters here. And that would tell us, okay, yes. Let's see. The depth at which the focal zone ends, which is going to be 10 centimeters. Did you students get that?
Yep.
Yes. Yes.
At least for now, right? Okay. Question number 7. Now, at which of the following depth is the beam narrowing? Now, guys, please, yes, okay. Narrowing. And what does it mean to narrowing? That it is still getting narrower and narrower and narrower and narrower. Or less and less and less and less in its diameter. Did that make sense? No, good. So 6 centimeters, 8 centimeters, 12 centimeters, 10 centimeters, 9 centimeters. And guys, We can say it's okay, we just mark, we say it's okay, this here is 6 centimeters. This point here is 8 centimeters. We can say it's okay, this point here is okay, maybe 10 centimeters. And we can say it's okay, this point here might have been 9 centimeters. So the point at which is okay, the beam is still narrowing is 8 centimeters. Is that clear?
Yes.
Okay. Because at this point, and okay, beyond that, it is still narrowing. Okay. Now, if I just switch the wording a little bit and say, it's okay, at which point is the beam at its narrowest? And you still had the same options. What would have been your answer? If I said, at which point or which depth is the beam at its narrowest? What would have been your answer?
B.
Armida?
B. 8 centimeters.
8 centimeters. Okay. You say 8, I don't know. Okay, so 8 centimeters. That's going to be the point where the beam is at its narrowest because that's the depth at which we had the focus. Did you guys get that?
Yep.
Yes.
Good. Now the next question, which is question number 8. Now what is it that it says? Okay, at which of the following depths is the beam widening? Or we can say it's okay, diverging. Clear? Okay. Okay. So yes, okay, what have they given us? Okay, they've given us a depth of 2 centimeters. Let's say, okay, this is 2 centimeters. We can say it's okay, 4 centimeters. Okay, yes. We can say 6 centimeters. We can say it's okay, 8 centimeters. Or we can say it's okay, 9.7 or 375 centimeters. So the depth at which the beam is narrow as widening is going to be this one here. Or the cheat is you can make it as okay, any distance or any depth at which falls into the far zone is going to be as okay where the beam will be widening. Clear? Okay. Any depth or distance that falls in the near zone is going to be as okay a point where the beam will be narrowing. And the focus is going to be as okay where the beam is at its narrowest. Did that make sense? Okay, guys. Now, which of the following depth is the beam most likely going to have the same diameter as it has as a depth of 11 centimeters? Now, you guys don't mind if I go to another slide, right?
No.
Good, that's fine. 12 millimeters. Now, what they mainly say here is throughout the entire course of the beam, from here to yes, okay, wherever. Okay. At what depth is it most likely going to have the same diameter as it has at a depth of 11 centimeters? So you can mainly say, okay, this distance maybe is okay at a depth of 11 centimeters. Did that make sense? So what they're asking is okay, at what part or what distance of the beam will it have the same diameter that it has at this depth here of 11 centimeters? Now you can mainly as okay, just look at it in this way. You call okay. We can say okay, what we know here, although not necessarily, but we can say okay, the diameter is going to be as okay, 6 millimeters. Okay, but just look at it in this way, guys. What is this distance? What do you think this distance here will be? From the focus, sorry, to the distance that we are asked about. Anybody? Is this real or I'm just having a nightmare?
10 centimeter.
Okay, guys.
Oh, sorry. I thought you were asking.
I'm
Like-
asking what is this distance here?
Got it.
3 centimeters?
Huh?
3 centimeters?
3 centimeters. Now, Lilia, do you want to tell us how you got that?
Because 10 centimeters was the focal point. So 11. Oh,
Let
no,
me get
8.
chance.
Sorry.
Oh, yeah. Okay.
So 11 minus 8 is 3.
So, what would that mean? That would mean, yes, okay, I'm asking you, yes, okay. So here is okay. This would be yes, okay. But again, yes, okay, you can just say, yes, okay, this was the distance in the far zone. Where, okay, yes. 3 centimeters into the far zone. Okay, so the diameter of the beam at 11 centimeters, which is 3 centimeters into the far zone, is going to be the same if we go 3 centimeters back from the focal point into the near zone, which is going to be 8 minus 5. 8 minus 3, sorry, which will become 5 centimeters. So at a depth of 5 centimeters, the diameter of the beam, yes, okay, we measure it here, at this depth here, is going to be the same as it was at a depth of 11 centimeters. If I just play a little around with the numbers and said, okay, yes, what do you think would have been is okay, the diameter of the beam at a depth of, let's say, it's okay, 14 centimeters. Not okay. What we had. What's going to have is okay the same diameter of the beam as on 14 centimeters. What will be your answer then? We go all as okay the way to 14 centimeters. The cheat is the same, lady, guys. You just have to calculate this distance. How do you do that? You subtract
6 centimeters.
and then you go and say, okay, 6 subtracted from 8, so that's okay at a depth of 2 centimeters. Did you guys get that? Now
Yeah.
the last question is, which of the following term does not belong? And what do we have? We have focus. We have, okay, we can say, it's okay, end of the near zone. We have, okay, yes, end of from upper zone. And we have, yes, okay, middle of focal zone. Now we don't necessarily, it's okay, have to look at the diagram. All right, we can still do it. We can still say, okay, let's say it's okay, this is our PCT. And just so we have, okay, yes, colors to refer to. This is your near zone, right? Clear, okay. You can say it's okay. This is our focus. And we can say that this here is your Fraunhofer zone or far zone. Yeah, okay. Now, out of all these terms here is okay. And we can say, okay, this here was your focal zone. Now, out of all these terms here, there's going to be one that is different from the 3 others. Now, when we say focus, that refers to this point here. Did that make sense? Even as okay, when we say as okay, the end of your near zone. What do you have at the end of your near zone? What do you have at the end of your near zone? The point where your near zone ends is what you call the
Focal point.
focal point. Okay. Can focal point go under another name?
Yeah, focus.
Focus. Okay, the focal point is just the point at which you focus. Clear, okay. You may read a paragraph, but there's going to be one sentence or one point of that paragraph that may catch your attention, right? And I say, just let me be for a sec. Let me just focus on this thing here, because I just found something interesting. Clear, okay. So the point on which you focus is going to be your focal point. But focal, if you look at it, it just means pertaining to focus. Clear? So in a field, the point that you focus at is the focal point. So where do we find that? Don't we find that at the end of your near zone? Where we say it's end of Fraunhofer zone. Or we can say, this is your Fraunhofer zone. This is going to be the end of your Fraunhofer zone. That's not your focus. And then they say it's the middle of the focal zone. The middle of your focal zone is again going to be your focus. Because that's we said we had a focal zone of whatever is 4 centimeters, but when we say it's half of that is in near zone, half of that focal zone falls in the far zone. But what's going to be in the middle between those two halves is going to be your focus. Did you guys get that?
Yep.
Good. But please, 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 please make sure that you know that near zone also is called near field. That's pretty obvious. But also goes under the name Fresnel zone. So had it say it's end of Fresnel zone, well, that'll still be the same as the end of the near zone. Did you guys get that? If you don't know, the Fraunhofer zone was a name for your far zone. You might think of that, also being focal point. Especially if you're going to fuel Fraunhofer and Fresnel. Clear, okay? So yes, things that goes under more than one name. Please make sure that you know all of the names. Or nicknames or synonyms or whatever you want to call them. Or akas. Clear? So what's another word for focal depth? Focal length. Clear? Focal depth and focal length. And how is that measured? Using what unit?
Centimeters.
Huh?
Sorry. Centimeters.
Any unit of distance, right? You can say inches. Is there anything wrong in measuring it in inches? No. As long as it is a unit of distance. Or unit of length. But that's why we say, you focal length or focal depth. The reason that we use as, okay, depth here is that, okay, yes, when we look at an ultrasonic image, or okay, you can say, okay, these points here marks different depths. But you may say it's okay, we focus at this depth here. At this depth here, which, okay, because that would have been 3 centimeter, that becomes just, okay, your focal depth. If you want to, yes, okay, you can focus here, which has become 4 centimeters. So this becomes just, okay, you focus at a depth of 4 centimeters. Or you can focus at this depth here. Because what is that all these points here mark? They mark different depths. Right? Where you can say, okay, this is going to be a shallow depth, and this is going to be the deepest. And as we go from here to here to here to here, we just go deeper and deeper and deeper and deeper. But these depths here are going to, as okay, be represented by length or distances. Did I make myself clear? Okay. Any questions?
No.
No. Could something else be used to, yes, okay, explain focus or focal point? Any other option? If we say A, B, C, D may not be enough. Any other point that would explain your focus?
The very beginning of your far zone.
Beginning of far zone. Okay, very good. Anything else that would explain your focus or focal point? Any other wording, statement, thesis that will say, okay, it's talking about the focus or focal point?
The middle of the focal zone.
Well, okay, that's already given there, my dear. I'm talking about something else, which is not given here. That still will, that's okay, explain your focus. Students, what happens to the beam at the focus?
The narrowest point.
Exactly at the narrowest part of the beam, right? Okay. Good. What else?
Be the spatial peak.
Pump it up.
It'd be the spatial peak.
Okay, you can say it's okay, the point with the highest intensity, right? The point of the beam with the highest intensity. Clear? Okay, so all those, what do they represent? Focus. Okay, and the point at which the beam focuses is the focal point. The depth at which the beam focuses is the focal depth or focal length. Clear? Did you guys get that? Or are you guys now unable to focus? Okay, okay. Get some glucose. Or let's say it's okay. Go and have some goodies. And okay, what I will be doing when we come back. We're going to be as okay, finishing, okay, yes. 1, 2, 3, 4, 5. 5 pages in one slide. Okay? 5 pages in one slide. Or maybe that'll become 2 slides, but it's better just, okay, just have 2 pages or 2 slides rather than 5 pages. Okay? So yes, okay, in between each bite, try to focus on your focus depth, focal points, focal lengths, divergence, far zone, near zone, things like that. Okay, so I see you guys back at 1 o'clock. Is that a fair deal? KK. Have fun till then, guys. Okay, students, welcome back. And now, any questions? No questions? Good. So let's see how we that's okay. Makes or how we make 5, 6 pages into 1 page. Now the first thing that okay, there may going to be 2 things that we will talk about. Because there's okay. Focal depth. Clear, okay. How is focal depth determined? Okay, now what do we mean by focal depth? The depth at which a beam will reach to its narrowest or to a focus. Clear, okay. The second thing that we will talk about, or it says, okay, it's going to be as okay, because it says, okay, divergence of the beam. Did you guys get that? Now, if you look closer at these 2 things here, your focal depth is mainly going to be as okay, be relevant to yes, okay, to your near zone. Clear? Okay. Whereas, okay, yes, the beam divergence is mainly going to be or relevant to the far zone. Clear? Because if you look at a beam, let's do it this way. And say, well, okay, yes, we have a PCT, we have a beam. Now this here is okay, so this was your near zone. Okay, and all dependent upon is okay how long or big your near zone is going to be, yes, okay, that will determine the focal depth or the depth or the length at which the beam will focus. Yeah, okay, the second thing that we may be talking about is, okay, what's going to be the factor that will determine that is going to be, is, okay, the divergence of the beam. And what did we say that the divergence of the beam was? Doesn't mean it's okay, just how the beam spreads out. Or you can say it's okay, increase in its width and height. Okay, well, where was it that this divergence of the beam happens? It happens in the far zone. Did you guys get that?
Yep.
Yeah.
Now, guys, when we talk about, yes, okay, the focal depth. Oh, let's do it this way. And oh, yes, okay, if we talk about the beam divergence. Okay, now they are both going to be, yes, okay, related to two things. One is going to be, yes, okay, diameter. Now, what we mainly mean here is going to be, yes, okay, the diameter of your PZT or active element or crystal or whatsoever. Is that clear? The next one is going to be, yes, okay, your frequency. Now, please, guys, when we say frequency, yes, okay, what we mainly just mean is going to be, yes, okay, the frequency of the transducer. Yeah, okay, not the frequency of your pulses or your pulse repetition frequency, your plain frequency of the transducer. Yeah, okay. And even when we talk about, yes, okay, the divergence of the beam, that as well is going to, yes, okay, be determined by the two features, which is going to be, yes, okay, the diameter of your PCT and or the frequency of the transducer. Did you guys get that?
Yep.
Yes.
Now, how is it that these relationships here are going to be? Now, your focal depth is going to be, as okay, there. Let's just let's just make this in a different color so we can. So what we mainly can say is that, okay, yes, the focal depth is going to be directly proportional to your diameter of the PCT. And we can also say that, okay, yes, the focal depth is going to be directly proportional to the frequency of the transducer. Right. Okay, now if you look at each of these here as, okay, individually, what would that mean? That we can say is, okay, if you, for instance, okay, have two different transducers. Now let's just say that, okay, yes, in this case, yes, okay, these two transducers here have, okay, yes, the same frequency. Let's just say, yes, okay, 2 megahertz, for instance. Just an example. So the frequency of this transducer and this transducer, both of them are going to be the same. It's going to be 2 megahertz. But various, okay, in one case may say, let's just do this way. That one transducer is going to have a big shape PCT. And the other one is going to have a small PCT. So the one with the big shape PCT is going to have a greater focal depth. We can say it's okay here, this PCT wall, let's say it's okay. 5 millimeters, and we can say it's okay, just to give a number, we can say it's okay, the focal depth was 5 centimeters. Whereas, okay, here, if this is a small PCT, let's say it's okay, 2.5 millimeters, then okay, yes, it might have had a focal depth of 2.5 centimeters. Did that make sense? So as far as, okay, yes, the frequency of the, the focal depth, we could say as okay, that was going to be as okay, directly proportional to the diameter of the transducer. Okay, but saying as okay, simply it's okay, we want to establish the relationship between the focal depth and the diameter of the PCT. Solely and solely will keep us okay, this here constant. Did you guys get that?
Yeah.
Now, on the other hand, if you then just say it's okay, let's just look at okay as the relationship between the frequency of the transducer and the relationship to focal depth. And since we said that okay, yes, they will be directly proportional. Okay. But we can still say as okay, now we is okay, just to establish this here. We can say it's okay that we have two transducers with similar size PCTs. Let's say it's okay that in both cases it's okay, they were 5 centimeters. Clear? Okay. But in one case is it that we have a high frequency, let's say 10 megahertz. Whereas, okay, yes. On the other hand, yes, okay, we may have a low frequency. Let's say 5 megahertz. Now, since they are directly proportional, we can say, okay, in this instance here, okay, we may have, okay, yes, greater focal depth. Let's just say it's okay that the beam focuses at a depth of 10 centimeters, where here we will have a shallower focal depth. Of 5 centimeters. Did you guys get that? Yes.
Yeah.
So as far as your focal depth is concerned, which is mainly as determined about it's going to just be related to what happens to the beam in your near zone. Right, you can say that is going to be determined by two factors. Factor one is how big is it that our PCT is? And the second is what is the frequency of your transducers? Did you guys get that?
Yep.
Okay, and here is your relationship between focal depth and diameter of PCT, focal depth and frequency of transducer was directly proportional. Now we can also put it this way and say that, let's see, that yes, always there at your near zone. Or yes, if you talk about focal depth or focal length is going to be let's say it's related to another thing, which would be convergence. If you don't like the word convergence, you can say it's narrowing of the beam. Or let's say it's focal depth. It's probably easier. Now your focal depth, that is going to be inversely proportional to the convergence of the beam. Why? Because in case where the beam converges to a greater degree as over here compared to here, you have a shallower focal depth. So you can mainly say as if you have a great convergence, just a sec, guys. Thank you, Dan. So what we can say is where we have a greater convergence of the beam. That would mainly mean that yes, you have a smaller, or we can say it's shallower focal depth. Whereas where we have a lesser convergence of the beam, we have a greater focal depth. Did that make sense?
Yeah.
Any questions? Okay. So the type of question that you can be asked is, okay, as which transducers will have shallower focal depth, greater focal depth. Okay. Similar to, yes, okay, let's just say, okay, what was it? Speed's relationship, propagation speed relationship to density and what was it? Stiffness. Or as we talked about yesterday, frequency of pulsed wave transducer related to stiffness, no, not stiffness, sorry. Propagation speed in PCT and the thickness of the PCT, right? Clear, okay. Any questions? Any questions, guys?
No.
Good. Now, the other thing that we as okay might be looking at was going to be as okay divergence of the beam, right? Okay. Okay. And it's going to again as okay be determined by the same two vectors. Okay. It's going to be as okay determined by the same two vectors. Okay. But, and if you look at, okay, where is it that the beam diverges? That will mainly as, okay, something that happens in the far zone. What did we mean to diverge? Mainly as, okay, that the beam spreads out. But how is it that it's going to just, okay, the divergence of the beam is going to be related to the diameter of the PCT and the frequency of your transducer? And guys, is it going to be inversely to that? Did you guys get that?
Yes.
Good. So what does that mean? Now we can say as okay that we got, let's say as okay, shoot two transducers. Okay. And when we say as okay, we have let's just make it a little bit colorful so we can see. Now we may say that okay, yes, we have a big PCT. Let's say as okay, just 5 centimeters. Now, of course, that's okay. It's going to have okay, yes, it's near zone, but right now we're not talking about the near zone. We are more talking about what's going to happen in the far zone, which is going to be the divergence. But as you can see, it's okay over here. We may have okay as let's say it's okay a small PCT. Let's say that this is just 2.5 centimeters. And of course, that's okay. We're going to have okay as near zone or with a certain focal depth. But the thing that we mainly will talk about here is going to be okay, how is that going to affect your divergence of the beam in the far zone? So what we mainly see, since they're going to be inversely related, we can mainly say that okay, yes, the beam with a greater PCT is going to diverge slowly. Whereas okay, the beam with a small PCT is going to just okay have a greater divergence. Yeah, okay. Or if we just put these two here as okay, we can say as okay side by side. or is okay in one case. We can say that, let's just say it's okay. This for the focal point, but anyways, less convergence or less divergence, sorry, will be this one here. Whereas, okay, if we had a greater divergence, sorry, the beam would go like this. Did you guys get that?
Yeah.
Good. Now we can just say, yes, okay, the same, yes, okay, may apply for your frequencies. Okay. Now let's just say that, okay, yes, we have, and please keep, yes, okay, since here is okay, diameters of, it was the diameters of the PCTs that we talked about. Okay, where we come in, it says, okay, a greater PCT, lesser divergence, a smaller PCT, greater divergence. But that was okay, yes, if the frequencies were the same. Let's just say it's okay that we had frequency of 5 megahertz and 5 megahertz for both transducers. Did you guys get that? Whereas, okay, now when we're going to just, okay, establish the effect of the divergence of the beam based on the frequency, we can say it's okay, we keep the diameter the same. We can say it's okay, 5 millimeters, for instance, 5 centimeters, 1.22. So 5 millimeters. Did you guys get that?
Yes.
Okay, but where we can mainly say is, okay, now one transducer is going to have a, let's say it's okay, a high frequency. Let's say 10 megahertz. Okay. Now let's just say it's okay. Well, okay, we have the near zone. We're not going to be focusing much upon that one now. But we can say since we have a high frequency, that's going to be it's okay. Less degree of divergence of the beam in the far zone. Whereas over here, we have a low frequency transducer. Okay, let's just say it's okay, 5 megahertz. Okay, now we have our okay near, so we're not going to be bothering much about that one because our main focus is how much does the beam diverge. So that's going to be okay due to a lower frequency. There's going to be a greater divergence. Or as we say, it's okay if we put these two here, it's okay, side by side. This is our focal point. We can say it's okay. Low frequency, less divergence, higher frequency, greater divergence. Did you guys get that?
Yeah.
Okay, guys. So, but, in all this, yes, okay, the main thing that is going to be as okay relevant is to, remember that, okay, as focal depth is directly proportional to both diameter of PCT and the frequency of the transducer. Whereas we say is okay, beam divergence is going to be inversely proportional to the same vectors. Diameter of PCT and frequency of transducer. What does it mean to be directly proportional? That when one or both are high, is going to increase. Whereas, okay, if one or both is low, it will decrease. What would it mean to have a greater focal depth versus a lesser focal depth? That, okay, yes, a lesser focal depth may be like this, whereas, okay, yes, a greater focal depth may be like this. Whereas, okay, when we look at, okay, yes, the divergence of the beam and its relationship to these two factors, they are going to be inversely proportional with mean. If we have a lower frequency, or a little smaller PCT, and or a transducer with a higher frequency, that's going to be as okay a greater divergence of the beam. Where does that occur? In your far zone. Clear? Likewise, if you had a narrow, if you had a greater PCT or a transducer with a higher frequency, there will be as okay a lesser divergence of the PCT. Did you guys get that?
Yeah.
Yes.
Good. And one thing that is going to be important or become important is that we see as okay, this high frequency leads to lesser divergence. Let's just look at it in context to as okay transducers. Where we see as okay, now here is okay, not to bother much about the near zone or focal zone, but what we mean is okay, what's going to be as okay, a greater divergence is going to be as okay if the beam goes like this versus it's okay, lesser divergence if the beam goes like this. And the lesser divergence in the far zone is ideal. How do we get that? By a high frequency transducer. Yeah, okay. This is mainly as okay going to cause or mean that okay, yes, that's what mainly is okay what we'll be striving for. Okay. And that's why you say it's okay, high frequency transducers are best. Okay. But please, 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 guys, keep in mind here is okay what we talked about is if we had a circular shape PCT, or what they call as okay a disc shape PCT or crystal. Clear? Okay. But where you can say is okay in those instances, okay, the height of the PCT is going to be equal to its width or breadth. Right? Okay. If you take a coin, any coin, and I say it's okay, do you mind measure it's okay its height? You say yes, okay, I measured it, and okay, yes, what I found is that okay, the distance from here to here is less than 5 millimeters. And then I say, okay, listen here, do you mind, yes, okay, measure the width? And you measure from here to here. And you say, well, okay, yeah, this is also 5 millimeters. Clear? Okay. But, all that's okay. It's going to become relevant later on. But most of our crystals are not going to be like this. They are rather going to be like this. Where we then can say, yes, okay, this may be the height. We can say, okay, the height maybe is okay, 5 millimeters, or let's say it's okay, 2 centimeters, for instance. Or whereas, okay, as the width is going to be only as okay, 1 millimeter. Okay. Now, when we say, yes, okay, convergence, now, guys, please look here. Please look here for a second. Now, when I say convergence of the beam, now convergence that's going to happen both like this and like this. Did that make sense? Clear? Likewise, when I say divergence, it's going to happen like this and like this. So horizontally and vertically. Did you guys get that? Clear? So the degree of convergence and or divergence of the beam is going to be as okay related to the, or okay says okay, frequency. That's going to be the main determining factor. Okay. We'll get to that later on. And of course, that's okay. We can say, it's okay, now what is it that we mainly also want in? Another thing that's okay as far as our PCT size are concerned. It's okay, we want what's going to be as okay ideal as far as the PCT size is concerned is we want a mainly okay, where are we? Okay. A smaller size PCT. Yeah, okay. Now, guys, if you look on page 137, you can maybe that's okay, just avoid that page, okay? The main thing is these relationships here. Yeah, okay. So you don't really need to bother yourself with the equations on page 137. Just remember the relationships that we got here. So yes, okay, 4 or 5 pages brought onto one slide. So make okay as a poster of that, and okay, as put it on the door of your whatever, on the refrigerator or something. Yes, okay, someplace that you look at quite often. Clear? All clear.
Crystal.
Crystal clear. Okay, good. If you want to talk physics, all clear.
PZT.
PZT clear. Here you go. Good. Okay, guys. Now, some of you may be scratching your heads and say, why in the do we need to know about it? Okay, diameters of the beam. Things like that, right? Okay. Okay. Now, in a later chapter, and probably that's okay, something that we're going to just okay be hearing a lot about is that diameter of your beam at different points may actually is okay affect or have an influence on what we'll call your lateral resolution. Or let me put it this way, the width of your beam is going to affect your lateral resolution. The height of your beam is going to affect your elevational resolution. And then the length of your pulse will determine your axial resolution. And you say, well, okay, on New Year's night, I only made one resolution. Where in the hell did the two other resolutions come from? Okay. So, good. But did you guys get this concept here or these ideas here? Okay. So, okay, tomorrow we talk about, yes, okay, tomorrow we go over these questions related to, yes, okay, focal depth and beam divergence together. Then there's a little concept of, okay, it's what we call the Huygens principle. Clear, okay. And I think, yes, okay, that's all that we have left in this chapter here. Yeah, okay. What is it tomorrow? Friday? Okay, and then we can go on to, let's say, yes, okay, look at the chapters. Oh, not chapters, sorry. Questions, yes, okay, related. There's some scene block. Okay, good. Good. We have some questions here, and then we probably also have some questions at the end of the book. So yes, okay, we can talk about those. Clear, okay? Does that sound fair? Good. Now, one thing that I would recommend is please try to read on your anatomy of the beam. Clear? Okay, if there's still any point that's not clear, please ask now. So you guys somehow know the different zones, points, lengths. What's the general concept of OKS diameter? Clear, okay. And what can we say? And then OKS, the relationship of the focal depth to frequency and diameter of PCT, the relationship of frequency, beam divergence to frequency and diameter, right? Yeah, okay. And before us, okay, talk about Huygens principle, which is okay, our next topic. Please just look at interference. You recall that, fellow? Good. Because that's pretty much okay, that's all what this Huygens principle is about. So if you haven't forgot about interference, okay, yes, you're good. If you have forgotten about it, well, okay, just look at it. Okay, guys? Then stay blessed, stay warm, stay dry, and take care of yourselves, okay?
See you
See you
tomorrow.
tomorrow.
Okay, check it out.
Bye.
Bye-bye, dear.